Hello, class. So I think I'm going to go ahead and get started. Hope everyone's doing well. Um, all right. So what I would like to do first is just kind of review what we did last time. And so we're going to review that by way of an example of simplifying an electric circuit. So let me draw a circuit here. Okay. All right. So, and then this is an 18-volt battery. Okay, so we have a circuit here with a number of resistors, and what we want to know is what is the current that flows out of the battery, okay? And so the strategy that we developed last time was that we want to identify series resistors and parallel resistors and keep combining all the resistors together until we just have one equivalent resistance. And then once we have that single resistor, we apply Ohm's law. Okay? So the first thing I see is that we have these two resistors are in series and these two resistors are in series. So to remind you what a series connection looks like, you have one resistor connected to another by a wire with no forking. Okay, so that is the important thing for identifying if two resistors are in series or not. Okay, so if you can go from resistor 1 to resistor 2 without the wire forking, then they are in series with each other. Okay, so for example, I can't go from resistor 4 to resistor 7 because the wire forks here and it forks here. So that's two forks along the path from those two resistors. But if I go from the 4 to the 15, there's no forking in this wire. Okay, so if you have two resistors that are in series, they are equivalent to a single resistor, which is the sum of the two resistances. And you can have more than two resistors in series. And so you just continue that pattern of adding them all together. So what that means is that these two resistors would combine to make a 19 ohm resistor. That's 4 plus 15. And these two would combine to make a 15 ohm resistor. That's 10 plus 5. So now I redraw the circuit, and when you redraw, you take any one of the two resistors and you just remove it, replace it with a wire, and then you replace the other one with the equivalent resistance. So I'm going to remove that one and just make it a wire, and then the remaining resistor, I just make it the equivalent resistance, 15 ohms. Okay. So now we encounter another type of connection between resistors, which is called a parallel connection. And so a parallel connection has a wire, and the wire forks into two or more pieces. You have a single resistor in each branch, and then it comes back together. So one of the things that you can see about a parallel connection is if you have a parallel connection, you can do a loop in the circuit where only the two things are in that loop. So if you can do a loop in the circuit with only R1 and R2, then they are in parallel. Okay? And the formula for a parallel resistance is 1 over R sub P equals 1 over R1 plus 1 over R2. Plus, if you have more than two in parallel, which you can, as we'll see in a moment, you just continue that pattern. So actually, the 19 and the 20 are in parallel, because if I go around this loop in the circuit, I only have the two resistors, okay? Even though the 20 is pointed in the same direction as the 7, they are not in parallel, because if I did this loop, see how it has the 20 ohm, the 7 ohm, but it also has the battery. So the 7 and the 20 are not in parallel. However, the 20 and the 15 are in parallel. Why? Because I could do this loop right here. And see how that loop, if you were walking on that loop, you only have those two resistors that you encounter. Okay? Similarly, the 19 is in parallel with the 15. So if I go around this outer loop, I only encounter the two resistors. So all three of these are in parallel. So I'm going to use the version of this equation with 3. 1 over R sub P is 1 over 15 for the first one, plus 1 over 20 for the second one, plus 1 over 19 for the third one. So if I add those up, we get 0.169. And a really common mistake that students make is they forget that this is the equation for 1 over the parallel resistance. So to actually get the parallel resistance at the end of the calculation, you have to do 1 over that to get R sub P. And that gives 5.9 ohms. So now I'm going to replace all three of these with just a single resistor. So get rid of this one and this one, replace the 20 with 5.9 ohms. All right. And now on the face of it, it looks like the 7 ohms and the 5.9 could be in parallel. but we can check that they're actually not in parallel, because if I do a loop with the 7 ohm and the 5.9 ohm, this is the only loop that I can make. And that loop is always going to have the 7 ohm, the 5.9 ohm, and the battery in it. So it's got 3 things, not just the 2 things, so it can't be parallel. But it is series, because if I go from here to here, the wire has no fork along that path. It does have bends, but it doesn't have forks. So this is series connection. R sub S is 7 plus 5.9 equals 12.9 ohms. So now I redraw the circuit one last time. And I want you to remember that these resistors all have their individual identities, but we're looking at this from the perspective of the battery, okay? And the battery sees all of these resistors just like a 12.9 ohm resistor, okay? So once we once we have it just down to one resistor in the battery, then we use our third main equation from the other day, which is called Ohm's law, and V equals IR. And so the voltage that the battery is providing is 18 volts. The current is what we're trying to figure out, and the resistance is 12.9 ohms. Solve for the current, and we get 1.39 amps. So that is a review of what we discussed last time. So I hope if it didn't make sense last time, it makes more sense this time. All right. So today's lesson is about power in the physics sense. Okay, I was actually in my Spanish class and I used the word poder for power, but I used it for power in the electrical, mechanics, physics sense of it. But poder is, I guess, apparently poder means power in more like the political sense. So if you, but we use the same word. So political power, electrical power, it's a completely different idea, but same word. Okay, so we already talked about power in the context of intensity of waves. But I'm just going to go over that again because that part was really quick. So power is the work done divided by the time it took to do the work. So it's the rate at which you do work. Okay. Now, this is for something that is outputting power. If you are outputting power, then you are doing work on your surroundings, giving your surroundings energy. Remember, work is transferring energy to something else, okay? So it's work done per time if you are outputting power, but if you are consuming power or using power, then it's the energy consumed per time. So this is if you are using power. So we have different things that are outputting power and using power. So for example, a light bulb is using power. It's not producing power. A solar panel is producing power. A battery is producing power when it's being used. If it's being recharged, it's consuming power. Okay? So it's kind of a matter of perspective. All right? And so I will write this variously as W over T for work per time, or I will write it as energy consumed per time for, you know, I'll write it in both ways. Looks like my pen just died, so let me grab another one really fast. Okay. All right. So from this equation, we can very easily get the units of power. And so the units of power, because it's an energy divided by a time, it's going to be a unit of energy divided by a unit of time. So units of energy are joules, units of time are seconds. So power is measured in joules per second. But this is called the watt, which is W. So 1 watt is completely equivalent to 1 joule per second. All right. So what we're going to do is we're going to talk about power in the general sense first, and then we're going to talk about power in the context of electric circuits. Okay. So so we're going to do some problems that are more from mechanics, not from electric circuits, to start off this lesson today. So let's do an example. An elevator has a mass of 250 kilograms. It is lifted 13 meters into the air in 7 seconds. What was the power output of the elevator motor? All right. And so one of the ways that we can calculate power, and this is a really useful way to calculate it, is to look at the energy gained by the object receiving the power. Okay? So look at the energy gained by the object that is receiving the power. So if we think about the elevator, the body of the elevator is gaining energy, okay? And because it's being lifted into the air, okay, it's going from y equals 0 meters to y equals 13 meters. The energy gained is gravitational potential energy, okay? So if I look at power is energy gained or energy consumed or whatever per time, we are gaining gravitational potential energy. We go from, and just to remind you, the formula for gravitational potential energy is mgy. So we start out with 0 gravitational potential energy because y is 0. And then we end up with not zero gravitational potential energy. So the energy gained is mgy. The time it takes is t. It's a 250 kilogram elevator. Gravity is 10. It is lifted up 13 meters above where it started, and the time elapsed is 7 seconds. And that is 4,640 watts. So that would be the power output of the elevator. Okay? Let's do another similar problem. Suppose that a car has mass 2,000 kilograms. The engine of the car accelerates it from 0 meters per second to 25 meters per second. And that acceleration takes 6 seconds. What is the power output? All right. So if we think about it, power is energy per time. So what type of energy is the car gaining? Well, it's getting faster, so it's gaining kinetic energy is the energy that it is gaining. And so because it starts out at rest, 0 meters per second, our initial kinetic energy is going to be 0 joules. But then it has a final kinetic energy of 1/2 mv squared. So that is 1/2 times the car's mass, which is 2,000, times the final speed of the car, which is 25 meters per second squared. Okay, so that is 625,000 joules. Okay, so when we calculate the power, power is energy gained, kinetic energy gained by the car divided by time it took. The car gains 625,000 joules in 6 seconds. Keep in mind that if the car accelerated from, like, let's say, I don't know, 5 meters per second to 25, it wouldn't start out with 0 kinetic energy. It would start out with a non-zero amount. And so we would have to get the energy gained, which would be the difference between these two numbers, okay? At any rate, 625,000 divided by 6 is 104,000 watts of power is the power output of the engine. If I convert that to horsepower, that's about 140 horsepower. So it's a pretty high performance car. Now this is something let's do a little calculation that I think is kind of interesting. What is the average power output of a Human. What is the average power output of a human? Well, here's something that's kind of interesting, okay? Food that we eat is chemical potential energy. All right? Food is chemical potential energy. Our body takes that chemical potential energy and uses it to do work on the environment, to do things, to write, to speak, to do everything. Okay? Now, what happens if I consume a certain amount of chemical potential energy, but I don't use it all? Okay? In that case, my body has to do something with that leftover chemical potential energy, and so it's going to turn it into fat, and I will gain weight. Okay? If I consume a certain amount of chemical potential energy and I use more than that amount, then hopefully my body's going to use all that energy that I ate today, but then it's going to reach into its energy reserves and take some of the fat and turn it into energy for me. If I have some. If I don't have some, then I'm going to begin to starve, okay? But if I have an extra storage of fat, my body can turn that fat into energy for me, and I can lose weight. So since most of us are maintaining a relatively constant weight, the amount of calories that you consume is equal to the amount of calories that you burn. All right? If there's an imbalance between the two, then you are either gaining weight or losing weight. So we can calculate the power output of a human by understanding that, so sort of steady weight, if you have a steady weight, then that means that your power output is 2,000 calories per day. All right? Calories are a unit of energy, different from joules, but it's a unit of energy, okay? Day is a unit of time. So this is energy per time. This is power, okay? And 2,000 calories is the daily recommended value for an average person, okay? People who are smaller don't need to consume as much calories. People who are big and tall and strong need to consume more calories, okay? So all we need to do is we need to convert this to watts. So I'm going to use the railroad method of unit conversion. And so I know that 1 calorie is 4,200 joules. That's just by definition. Okay. And I know that 1 day is 86,400 seconds. Okay. So day cancels day, calorie cancels calorie, and I'm left with joules per second, which is watts. And then I just have to do the multiplications and the divisions, and I get 97 watts. That is your average power output. Okay? So when you're sleeping, your power output is less than that. If you are talking or walking around and doing stuff, your power output can be much greater than that. But I think this is interesting because this is approximately the power output of an incandescent light bulb. Okay, pretty interesting. So there's another way that we can calculate power. So let's learn how to calculating instantaneous power with forces. So what I want to remind you about is work. work is equal to a transfer of energy. And so the picture you want to have when you're thinking about work is you have some force that is being applied to an object, and as a result of that force, it is displaced a certain amount. Okay. But in general, the force and the displacement won't be in the same direction. Okay. So in order to calculate work, what we do is we take the force and we make a force triangle. Okay. And there's a component of the force that is perpendicular to the displacement. There's a component of the force that is parallel to the displacement. And the work is force parallel times displacement. All right? So using that, power is work done divided by time. All right? Work is F parallel times displacement, and we divide that by time. Notice how I have displacement over time. That's velocity. So if you want to know what is the instantaneous power, it's F parallel times velocity. That's a nice, another fairly common formula. So, all right. Let's do another example using this formula. I'm going to draw the picture for this example up here. So we have a wall, and there is a box that is pinned up against the wall, and you are pushing on that box with a 300 Newton force. That force is applied at an angle that is 50 degrees above the horizontal. Now, obviously, because of the presence of this wall, the box can't move left-right. It's being pinned against the wall, but because this force is partially going upward, it can move upward. And that upward speed is 2 meters per second. So we want to know, what is the power output? What is the instantaneous power output of the person? Okay, so because the block is moving up and down, then F parallel is the component of the force along the direction of motion. So whereas in this little drawing that I made, F parallel was the horizontal component, that's because it was moving horizontally. But here we have it moving vertically, so F parallel is going to be the vertical component. So F parallel is going to be it's going to be 300 times, and you can see that it's opposite the angle, so that is going to be sine of 50 degrees, which gives about 230 newtons. And then power is F parallel times velocity. It's going to be 230 times 2, which is 460 watts is the power output of the person at that instant. Okay? So remember, 97 watts is the average power. So, when you're sleeping, it's less than that. When you are awake, it's more than that. And when you are awake and exerting yourself, it's even more than that. Okay? Okay, so now, by the way, I just want to make sure you guys understand the difference between um, energy and power. Power is the rate of consumption of energy. Okay. Um, and so we talked a little bit about this analogy between energy and money. Okay. So let me give you an analogy. Okay. What would something be like if they have a lot of energy but no power? That is like a retired person, okay? Because a retired person isn't making any more money. The rate of income, the rate of money coming in is zero because they're retired, okay? Let's forget about stocks and that kind of stuff. Like the rate of money coming in from labor, their own labor, is zero once they've retired. But because they've retired, they've saved a lot of money in the bank. So the money in the bank is like the total amount of energy, and the rate at which the money is coming in is like the power. And so the power is zero, but the energy is great. Okay. If you're a young person, you haven't had the chance to build up that bank account yet. So you don't have a lot of money, but you're in your prime earning age, so you're making a lot of money. So when you're young, it's the rate at which money is coming in is large, but the amount of money that you have saved up hasn't been built up yet. So that's like having a lot of power but no energy. And then if you are kind of like a middle-aged person, you've probably saved up a decent amount of money and you're making a decent amount of money, so you have both power and energy. Okay? So yeah, there's a difference. You could have energy with no power. You could have power with no energy. So now let's circle back to electrical power. Electrical power, the formula is I times V, where I is the current output of the source, and V is the voltage output of the source. All right? So that is electrical power. We could take this and we could use Ohm's law in the form V equals IR. And so we could replace V with IR. So we would get power equals I times IR equals I squared R. So that's an alternative equation for power. Or we could use I equals V over R. That's just dividing both sides by R in Ohm's law. And I get power is V over R times V, which is V squared over R. So these equations are also used, and whereas this equation is most often, they give the exact same answer. But this equation always works, even if you don't have a resistor. Whereas this like a battery, for example, doesn't have a resistance. So it wouldn't make sense to use this equation for power for batteries because batteries don't have power. Okay, so this is the power consumed by resistor. Okay, so let's just do two brief examples. So suppose I have a circuit that looks like this. and this is a 12-volt battery, and we want to know what is the power output of the source. Okay, so clearly these are 2 ohm resistors that are in series, so they are going to make 4 ohms. So I'm going to simplify it to one resistor. Okay. And then once I've combined those two, it's going to be in parallel with the 2 ohm. So I'm going to use 1 over R sub P is 1 over 2 plus 1 over 4. And that says that the parallel resistance is 1.3 ohms. So all 3 of those together makes a 1.3 ohm resistor. So if I want to calculate the current, I have V equals I times R. The battery is a 12-volt battery. The resistor, the equivalent resistance of that circuit is 1.3 ohms. And so I get 12 over 1.3. And that gives me about 9 amps is the current that flows. And then power is current times voltage. So that's going to be 9 amps flowed out of the source at 12 volts. So that is 108 watts is the power output of the battery. Let's do one more quick example. So this one is going to be an even simpler circuit. So we have 12 volts and then a 2 ohm resistor. But this 2 ohm resistor is representing an electric motor. Because remember, I said that resistors oftentimes represent something that's doing a useful task in the external world outside of the circuit. Okay? So this is an electric motor lifting a 1 kilogram mass. So my question is, how far vertically is the mass lifted in 3 seconds? Okay? And so basically, the power output of the battery is going to be equal to the power in to the mass. All right. Now the battery's power output, because it's connected to a single resistor, I'm going to use this V squared over R formula. All right. So V squared over R. And then if I look at the mass, this is analogous to the elevator problem. You have something lifted. So the energy that it's gaining is gravitational potential energy. Okay, so the power that it's gaining is gravitational potential energy per time. So this is our power equation for this problem. All right, and so plugging in numbers, we get the voltage of the source is 12 volts. The resistance is 2 ohms. It's a 1 kilogram mass. Gravity is 10. We're trying to calculate how far is it lifted up, so that's y. Leave it as a variable in 3 seconds. And so that gives us y equals 21.6 meters. Okay, So yeah, this is kind of cool because we're using power to connect multiple areas of physics. All right. So that is my